Opening, a moment of calm. Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through the cosmos, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest gently on a distant point and allow the story to unfold around you like a gentle tide. We're going to explore something so vast, so incomprehensibly large, that it challenges everything we think we know about size and distance. But don't worry about understanding every detail or remembering every number. Let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination. This is a story about discovery, about the human impulse to look up at the night sky and wonder what lies beyond, and about structures so enormous that they dwarf entire galaxies the way galaxies dwarf individual stars. So breathe, relax, and let's drift together into the depths of space, where the biggest structures we've ever discovered await. Introduction. The scale of wonder. There's something profoundly humbling about contemplating the universe. We spend our days moving through spaces we understand, rooms and streets and cities, places where we can see from one end to the other, where distances make sense in terms of footsteps and minutes. But the cosmos operates on an entirely different scale, one that doesn't just exceed our everyday experience, it shatters it completely. Tonight, we're going to journey to the edge of what humanity has discovered, to structures so massive that even seasoned astronomers struggle to truly grasp their dimensions. We're talking about galaxies, yes, but not the kind you might be thinking of. Not the beautiful spirals you've seen in photographs, their arms gracefully curving through space. Not even the giant elliptical galaxies packed with trillions of stars. We're talking about something else entirely. Something that exists on a scale that bridges individual galaxies and the largest structures in the universe itself. Imagine, if you will, that you could somehow step outside our Milky Way galaxy and look back at it from a great distance. You'd see a majestic pinwheel of light, hundreds of billions of stars arranged in elegant spiral arms, all swirling around a bright central bulge. The entire structure stretches about 100,000 light-years from edge to edge. That's the distance light traveling at 186,000 miles every single second covers in 100,000 years. It's a span so vast that if you started at one edge and traveled at the speed of light, you could watch entire civilizations rise and fall before reaching the other side. Now hold that image in your mind, that massive, incomprehensibly large galaxy, with all its stars and nebulae and star clusters and planets. Now imagine lining up not just 2 or 3 of these galaxies, but more than 160 of them, end to end, in a single continuous structure. That's the scale we're approaching. That's the size of Alcyoneus, the radio galaxy discovered in 2022 that held the record as the largest structure ever created by a single galaxy. But the story doesn't end there. Just 2 years later, in 2024, astronomers discovered an even larger structure, a radio galaxy called Porphyrion, stretching an almost inconceivable 23 million light-years across space. And then, later that same year, they found something even bigger still, a structure designated TXS0033 plus 252, spanning 26 million light-years, a distance so enormous that it represents a significant fraction of the cosmic web itself, the largest known structures in the universe. These discoveries are reshaping our understanding of how galaxies evolve, how black holes grow and influence their surroundings, and how the universe itself is structured on the grandest scales. They're showing us that the influence of a single galaxy, or more precisely, the supermassive black hole at its center, can extend across cosmic distances that dwarf everything we previously imagined. But to truly appreciate these discoveries, we need to start at the beginning, with the story of how they were found, with the people who made these discoveries, and with the remarkable technology that made it all possible. We need to understand not just the numbers, which can feel abstract and meaningless when they get this large, but the physical reality of what these structures are, how they form, and what they tell us about the universe we inhabit. So let's begin our journey, not with the largest structures, but with a graduate student in the Netherlands, looking at data from a radio telescope, searching for something entirely different, and stumbling upon one of the most remarkable discoveries in modern astronomy. The discovery, a serendipitous find on what seemed like an ordinary day in the Netherlands, a country better known for its windmills, tulip fields, and extensive canal systems than for cosmic revelations. A graduate student named Martin Oy sat at his computer, analyzing data from one of the world's most innovative radio telescopes. He wasn't searching for the largest galaxy ever discovered. He wasn't even looking for galaxies at all, really. Oy and his supervisors at Leiden University were investigating something entirely different, examining the distribution of matter in the cosmic web, those invisible threads of gas and dark matter that connect galaxies across the vastness of space. But sometimes, the universe has a way of revealing its secrets when we're looking for something else entirely. The data OEI was examining came from a remarkable instrument called LOFAR, which stands for the Low Frequency Array. Picture, if you will, not a single massive telescope dish pointing skyward like the ones you might have seen in movies or photographs, but thousands upon thousands of small antennas scattered across the European countryside like a constellation of listening posts. These antennas, numbering more than 70,000 in total, are distributed across the Netherlands primarily, but they stretch all the way from Ireland to Poland, from Sweden to Bulgaria, creating one of the largest scientific instruments ever built. Unlike traditional radio telescopes with their enormous moving dishes, LOFAR's antennas stand motionless. They're simple dipoles, metal structures that look almost unimpressive individually, standing in fields and meadows across Europe. Some look like inverted V shapes, others like tiles arranged in groups. But when their signals are combined through sophisticated computer processing, they create one of the most powerful radio observatories on Earth, capable of peering through dust and gas that would obscure optical telescopes, revealing radio emissions from objects billions of light years away. The way LOFAR works is quite different from conventional telescopes. Instead of physically moving to point at different parts of the sky, LOFAR uses digital beamforming. The signals from all these thousands of antennas are digitized, transported through fiber optic cables to central processing facilities, and then combined in software. By adjusting how the signals are combined, astronomers can effectively point the telescope anywhere in the sky without any physical movement. It's like having thousands of eyes looking in different directions simultaneously, with a computer brain that can focus all that vision on any point it chooses. LOFAR operates in a frequency range that had been largely unexplored before its construction, between 10 and 240 megahertz. These are the same frequencies used by FM radio stations on Earth, but LOFAR uses them to detect some of the faintest whispers from the cosmos. To produce a single image from LOFAR, more than 13 terabits of raw data per second, equivalent to more than 300 DVDs worth of information, must be digitized, transported, and combined. Supercomputers at the University of Groningen process this torrential flow of information, transforming terabytes of raw antenna data into science-ready images in just a few days. The telescope is particularly sensitive to diffuse extended radio structures, the kind that giant radio galaxies produce. Structures that had previously been too faint or too spread out for earlier instruments to detect clearly. This capability would prove crucial for Oe's discovery. Martin Oey had learned about radio galaxies in his studies. Of course, every astronomy student encounters these exotic objects. He knew that the largest known radio galaxy at the time, discovered before his analysis, stretched about 10 million light-years across, already an almost inconceivable distance, roughly equivalent to lining up 100 Milky Way galaxies end to end. But as he processed the LOAFAR data, applying new techniques to subtract interfering compact radio sources and enhance the visibility of diffuse structures, something unusual caught his attention. There, in the data, was a radio structure that appeared to stretch much farther than anything he'd seen before. It was a classic configuration: two enormous lobes of radio emission on opposite sides of a distant galaxy, like wings extending from a cosmic bird. But the scale was unlike anything in the records. The lobes seemed to extend across a truly enormous expanse of sky. Oey ran the numbers through an online calculator just to get a rough first estimate. The result made him pause and check his work. According to his calculations, this structure stretched approximately 5 megaparsecs across. For those unfamiliar with the cosmic measuring stick, a parsec is about 3.26 light-years, and a megaparsec is 1,000,000 parsecs. 5 megaparsecs works out to about 16.3 million light-years from one end to the other. Oy, still learning the ropes of radio galaxy research, wasn't entirely sure of the significance of what he was seeing. He sent an email to Martin Hardcastle, one of the world's leading experts on radio galaxies and a co-author on the study. Hardcastle's response was immediate and unambiguous in its excitement. "Congratulations," he wrote. "This is the largest radio galaxy ever found." The discovery was serendipitous in the truest sense of the word. Oey had stumbled upon this cosmic giant not through a systematic search for record-breaking galaxies, but as a byproduct of investigating something entirely different. It's a reminder that in astronomy, as in life, sometimes the most significant discoveries come when we're not specifically looking for them. The universe is full of surprises waiting in the data, hidden in plain sight, until the right person with the right tools examines it from the right angle. The galaxy that hosts this stupendous radio structure received the designation SDSS J08 1421 68 plus 520 2410 0. A string of numbers and letters that describes its position in the sky as catalogued by the Sloan Digital Sky Survey. But Oey and his colleagues gave it a more memorable name, drawing on Greek mythology. They called it Alcyoneus, after a legendary giant, the king of the Thracian Gigantes, who was said to be immortal within his homeland. In the myths, Alcyoneus was one of the Gigantes who fought against the Olympian gods in the Gigantomachy, the great battle between the gods and the giants. According to legend, he couldn't be killed while he remained in the land of his birth, but the hero Heracles dragged him beyond its borders and slew him. The name seemed fitting for a structure of such mythological proportions, a giant among giants in the cosmic landscape. Alcyoneus resides in the constellation Lynx, one of the fainter constellations in the northern sky, introduced by the astronomer Johannes Hevelius in the 17th century. He named it Lynx because, he said, you'd need the eyes of a lynx to see it. The constellation contains few bright stars, making it a challenge for amateur astronomers to locate. But within this dim constellation lies this extraordinary structure, invisible to our eyes, but brilliant when viewed through radio telescopes. The galaxy is located approximately 3.5 billion light-years from Earth. When the light we're now detecting left Alcyoneus, Earth was a vastly different place. Life was confined to the oceans. The continents were arranged differently. It would be hundreds of millions of years before complex life would emerge on land, before the first trees would grow, before dinosaurs would walk, before humans would evolve and build telescopes to look back across space and time to see this ancient light. The discovery paper, published in the journal Astronomy and Astrophysics in February 2022, presented not just Alcyoneus, but also revealed that the LOFAR surveys had detected more than 8,000 giant radio galaxies, many of them previously unknown. It was a treasure trove of data, suggesting that these cosmic giants might be more common than astronomers had previously thought. The survey had, in effect, opened a new window on the universe, revealing a population of enormous structures that had been hiding in plain sight, too faint for previous instruments to detect. But among all these discoveries, Alcyoneus stood out as the most extreme, the largest structure known to be created by a single galaxy. It was a record that would stand for just over 2 years before being surpassed. But its discovery marked a turning point in our understanding of just how large these structures could grow. The finding raised immediate questions. Why was Alcyoneus so large? What conditions allowed it to grow to such extraordinary dimensions? Was it simply older than other radio galaxies, having more time to expand? Was it in an unusually empty region of space, where its jets encountered less resistance? Or was there something special about the black hole at its center, some property that allowed it to maintain its jets for an exceptionally long time? These questions would drive further research, leading to more discoveries, including the even larger structures that would be found in the years to come. But before we can understand what makes these giants so special, we need to understand the scale we're dealing with. To build up a framework for comprehending distances that strain the very limits of human imagination. Understanding scale, from the familiar to the incomprehensible, to truly appreciate the size of Alcyoneus and the even larger structures discovered since, we need to embark on a journey through cosmic scales, building up from the familiar to the incomprehensible, step by careful step. Let's start with something we can at least conceptually grasp. The distance light travels in a year. Light moves faster than anything else in the universe, racing through the vacuum of space at approximately 186,000 miles per second. Think about that for a moment. In the time it takes you to blink, light could travel around the Earth's equator more than 7 times. In 1 second, light covers a distance that would take a commercial airliner more than 3 weeks to traverse. Yet even at this incredible speed, distances in the universe are so vast that we measure them in light years. The distance light travels in an entire year. In 1 year, light covers about 5.88 trillion miles. That number, 5.88 trillion, is already beyond our everyday experience. If you tried to count to 1 trillion, counting one number every second, it would take you more than 31,000 years. And a light year is nearly 6 times that distance in miles. It's a span so large that it makes the distance between Earth and even our nearest celestial neighbors seem tiny by comparison. The distance from Earth to the Sun, what astronomers call an astronomical unit, is about 93 million miles. Light crosses that distance in about 8 minutes. The farthest human-made object, Voyager 1, launched in 1977, is now about 14.5 billion miles from Earth, having traveled for nearly 5 decades. Yet, it's still less than 1,000th of a light year away. At its current speed, it would take Voyager 1 more than 70,000 years to travel just 1 light year. The nearest star system to our Sun, Alpha Centauri, is about 4.37 light-years away. If you could somehow travel at the speed of light, which physics tells us is impossible for anything with mass, it would take you more than 4 years to reach it. Yet even at that incredible distance, Alpha Centauri is practically next door on cosmic scales. Now let's step up to the scale of our home galaxy, the Milky Way. It's a majestic spiral of stars, gas, and dust, containing somewhere between 200 billion and 400 billion stars, each one potentially hosting planets of its own. The Milky Way stretches approximately 100,000 light-years from edge to edge. If you could somehow stand far above the galactic plane and look down, you'd see a beautiful pinwheel structure with graceful spiral arms curving outward from a central bulge, with a bar-shaped structure of stars running through the center. Our Sun sits about 26,000 light-years from the galactic center in a minor spiral arm called the Orion Spur, or the Orion Arm. We're located between two major spiral arms, the Perseus Arm and the Sagittarius Arm, in what you might think of as a galactic suburb, neither in the dense, crowded center, nor in the sparse outer reaches. To put the Milky Way size in perspective, if you were to board a spacecraft that could travel at the speed of light, a journey from one edge of the Milky Way to the other would take 100,000 years. Think about that for a moment. All of recorded human history, from the first written records in ancient Mesopotamia to the present day, spans only about 5,000 years. That's merely 5% of the time it would take light to traverse our galaxy. Entire civilizations could rise and fall, species could evolve, continents could shift, and you'd still be traveling through the Milky Way. Now, let's consider our galactic neighborhood. The Milky Way isn't alone in space. It belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. These galaxies are gravitationally connected, orbiting around their common center of mass, a cosmic family of sorts. The largest member of this group is the Andromeda Galaxy, also called Messier 31 or M31. Andromeda lies about 2.5 million light-years away from us. It's a galaxy similar to our own, perhaps slightly larger, containing roughly 1 trillion stars compared to our few hundred billion. On a clear, dark night, far from city lights, you can actually see Andromeda with your naked eyes, a faint smudge of light that's actually the combined glow of 1 trillion suns. What you're seeing when you look at Andromeda is light that left that galaxy 2.5 million years ago, long before modern humans existed. When that light began its journey, our ancestors were still early hominids, and it would be millions of years before our species, Homo sapiens, would evolve. The light crossing the space between our galaxies right now won't be seen by anyone for 2.5 million years, by civilizations we can barely imagine, if any exist by then. In about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger galaxy that some astronomers have already nicknamed Milkometa, or Milkometa. It will be a slow-motion collision spanning hundreds of millions of years, with the two galaxies passing through each other, their gravitational interaction stirring up stars and gas, triggering new waves of star formation, before they eventually settle into a single, larger elliptical galaxy. If we were to line up Milky Ways end to end, it would take about 25 of them to span the distance between us and Andromeda. That's the neighborhood scale we're talking about when we discuss the local group. These are distances that already strain comprehension, spans of space so vast that the fastest spacecraft humanity has ever built, the New Horizons probe that visited Pluto and continues into the outer solar system, would take more than 500 million years to reach Andromeda if it were heading in that direction. But now, let's talk about Alcyoneus. This structure, these radial lobes emanating from a single galaxy, stretches approximately 16.3 million light-years across. To put that in terms of Milky Ways, you would need to line up about 163 of our galaxies end to end to equal the span of Alcyoneus. Picture that for a moment. Take the entire Milky Way, with its hundreds of billions of stars, all its spiral arms and nebulae and star clusters and planets, everything we've been discussing, and then imagine another 162 galaxies just like it, all lined up in a row. That's the scale we're discussing. Or think about it this way. The distance from Earth to Andromeda, that span of 2.5 million light-years that represents our nearest large galactic neighbor, fits into Alcyoneus more than 6 times over. You could place the entire local group, our whole galactic neighborhood, with all its dozens of galaxies, within the span of Alcyoneus, with room to spare. Let's try another comparison, one that might help make this more tangible. Imagine you could somehow shrink yourself down so that you were standing at one edge of Alcyoneus, at the tip of one of its radial lobes. You look across to the other side, to the opposite lobe, 16.3 million light-years away. If at that moment, someone on the far side turned on an incredibly powerful lighthouse, bright enough to be visible across that distance, how long would you wait to see its light? The answer is 16.3 million years. When the light finally reached you, Earth would have changed beyond recognition. Species would have evolved and gone extinct many times over. Continents would have shifted positions. In the time it takes light to cross Alcyoneus, entire epochs of life on Earth would have come and gone. The dinosaurs lived for about 165 million years, but that's only about 10 times the light crossing time of Alcyoneus. Ice ages would have come and gone. Mountains would have risen and eroded away. Before Alcyoneus was discovered, the title of largest known galaxy was a matter of some debate, and it's important to understand why. Many sources cited IC 1101, a supergiant elliptical galaxy located about 1 billion light-years away in the constellation Virgo. IC 1101 is indeed immense in terms of its stellar content. Its core region spans about 400,000 to 600,000 light-years, making it 4 to 6 times wider than the Milky Way in its visible stellar component. The galaxy contains approximately 100 trillion stars, about 1,000 times more than our own galaxy. It's a dying galaxy, having used up most of its gas and dust, with very little new star formation occurring. The stars it contains are mostly old, giving the galaxy a yellowish hue rather than the blue tint associated with young, hot stars. At its heart lies one of the largest supermassive black holes ever discovered, with a mass estimated at somewhere between 40 billion and 100 billion times the mass of our Sun. But there was confusion about IC 1101's actual size, and this confusion is important for understanding what we mean when we talk about the size of galaxies. Some sources claimed IC 1101 stretched as far as 6 million light-years across, but these measurements included its very diffuse halo of stars, extremely faint light that's difficult to detect, and the vast cloud of intracluster light. This intracluster light consists of free-floating stars that have been stripped from galaxies and now wander between galaxies in the Abell 2029 cluster, where IC 1101 resides. When we measure the size of a galaxy based on its stars, we're essentially measuring where we can detect enough starlight to say the galaxy is still there. But that depends heavily on how sensitive our detectors are. A more sensitive detector might see fainter, more distant stars, making the galaxy appear larger. This is why astronomers use standardized measurements, like the radius within which half the galaxy's light is emitted, called the effective radius, or half-light radius. For IC 1101, the effective radius is about 212,000 light-years, meaning half of all the light from the galaxy comes from within this radius. But the full extent of its diffuse halo might stretch to 2 million light-years or more from the center. So depending on how you measure it, you could get different answers for how large IC 1101 really is. But here's the crucial point. When astronomers talk about the size of galaxies in terms of their radio emissions, which is what makes Alcyoneus so special, we're talking about something completely different. The radio lobes of Alcyoneus aren't filled with stars. They're not even filled with much visible matter at all. Instead, they consist of extremely diffuse plasma, ionized gas that's been accelerated to nearly the speed of light and then injected into intergalactic space by powerful jets from the galaxy's central supermassive black hole. This plasma glows in radio wavelengths, invisible to our eyes, but brilliant when viewed through radio telescopes like LOFAR. The lobes are so diffuse that if you could somehow fly through them, you might encounter only a few particles per cubic meter, making them far more tenuous than the best vacuum we can create in laboratories on Earth. In fact, they're more empty than the vacuum of space itself in most places. Yet despite their diffuse nature, these structures are real, they're energetic, and they're enormous. They represent one of the fundamental ways that galaxies interact with and shape their cosmic environment. The energy contained in these lobes is staggering, equivalent to the combined output of trillions of suns over millions of years. This energy didn't come from nowhere. It came from matter falling into the supermassive black hole at the galaxy's center, converted into jets of particles and magnetic fields through processes that represent some of the most extreme physics in the universe. Porphyrion and beyond, breaking records, but Alcyoneus's reign as the largest structure created by a single galaxy was destined to be short-lived. In September 2024, just over 2 years after Alcyoneus's discovery was published, the same team that found Alcyoneus announced an even more remarkable discovery. They had found a radio galaxy with jets stretching approximately 7 megaparsecs, or about 23 million light-years across. This new record holder was named Porphyrion, after another giant from Greek mythology, a son of Gaia, the earth goddess, who rebelled against the Olympian gods. Porphyrion's discovery pushed the boundaries even further than Alcyoneus had. It's not just larger than Alcyoneus, it's also more distant, located about 7.5 billion light-years from Earth. When we observe Porphyrion, we're seeing it as it existed when the universe was only 6.3 billion years old, less than half its current age of 13.8 billion years. Think about what that means. This enormous structure, spanning 23 million light-years, existed when the universe was young, when galaxies were still forming and evolving rapidly, when the cosmic web was still taking shape. This means that enormous jet systems like Porphyrion have existed for most of cosmic history, reaching across significant fractions of the universe's large-scale structure even in relatively young cosmic times. The universe at that epoch was smaller and denser than it is today. Galaxies were closer together. The filaments of the cosmic web, which we'll discuss in detail later, were more tightly packed. For Porphyrion's jets to reach 7 megaparsecs in this more compact universe means they extended across an even larger fraction of the universe's structure at that time. To match Porphyrion's span, you'd need to line up about 140 Milky Way galaxies end to end. The structure is equivalent to roughly 2/3 the radius of a cosmic void at the epoch when Porphyrion existed. These voids are the enormous empty regions between the cosmic web's filaments, the largest empty spaces in the universe. For a structure created by a single galaxy to reach across such a significant fraction of these cosmic voids suggests that black hole jets may have played a much more important role in shaping the large-scale structure of the universe than astronomers had previously appreciated. The discovery of Porphyrion came from the same OFAR survey that found Alcyoneus, but it required careful analysis to confirm. The team used not just LOFAR, but multiple telescopes to verify their finding. They used the giant microwave radio telescope in India to get additional radio observations. They used the dark energy spectroscopic instrument operating from Kitt Peak National Observatory in Arizona to help identify the host galaxy and measure distances. And they used the Keck Observatory in Hawaii to measure the precise distance to Porphyrion and to study the properties of the central black hole. What they found was remarkable. The jets came from a supermassive black hole at the heart of a galaxy about 10 times more massive than our Milky Way. The galaxy itself, while large, wasn't particularly exceptional. But the black hole had been active for approximately 1 billion years, steadily pumping energy into these enormous jets. For 1 billion years, matter had been falling into this black hole, being converted into jets of particles and magnetic fields, shooting out perpendicular to the accretion disk at nearly the speed of light. But the discovery of Porphyrion came with another surprise. Astronomers had generally believed that the largest, most powerful jets came from black holes in what's called jet mode, where most of the black hole's energy output goes into the jets rather than into radiation. But Porphyrion's black hole was in radiative mode, where most of the energy comes out as radiation from the accretion disk. This was unexpected. It suggested that the models astronomers had been using to understand these giant jets needed to be revised. The fact that Porphyrion came from a radiative mode black hole has profound implications. If radiative mode black holes can produce jets this large, and if they were more common in the early universe, as observations suggest they were, then there may be many more of these giant structures left to find. The sky surveys conducted so far have covered only a fraction of the sky. LOFAR, for instance, has surveyed about 1/8 of the sky. There could be dozens or hundreds of structures as large as or larger than Porphyrion waiting to be discovered. And indeed, later in 2024, astronomers announced the discovery of yet another radio galaxy. This one, even larger than Porphyrion, designated TXS0033 plus 252. This structure spans approximately 8 megaparsecs, or about 26 million light-years across. To put this in familiar terms, you'd need about 160 Milky Way galaxies lined up end to end to match this span. The numbers become so large that they lose meaning in conventional terms. When we say 26 million light-years, we're describing a distance that light traveling at 186,000 miles every single second takes 26 million years to cross. It's a distance scale on par with the cosmic web itself, the largest known structures in the universe. Think about what this means for our understanding of the universe. A single galaxy, through the action of its central black hole, can create a structure that spans distances comparable to the filaments connecting galaxy clusters. These aren't just local effects. These are cosmic scale phenomena, structures that bridge the gap between individual galaxies and the large-scale structure of the universe itself. The discovery of these giant structures raises profound questions. How common are they? Do all large galaxies go through a phase where they produce such enormous jets? Or are these rare events requiring special conditions that we don't yet fully understand? What role do these jets play in the evolution of the universe? Do they heat the gas in the cosmic web, preventing it from cooling and forming new galaxies? do they transport magnetic fields from galaxies out into intergalactic space, magnetizing the cosmic web? These are questions that astronomers are actively working to answer. But to understand the answers, we need to understand what these structures actually are, how they form, and what powers them. We need to delve into the nature of radio galaxies themselves. The nature of radio galaxies. Cosmic engines to understand what makes Alcyoneus, Porphyrion, and TXS 0033 plus 252 so remarkable, we need to delve into the nature of radio galaxies themselves. These aren't just large galaxies that happen to emit radio waves. They represent some of the most energetic and dramatic phenomena in the universe. Cosmic engines powered by the most extreme gravitational fields known to exist. At the heart of every radio galaxy, indeed at the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These aren't the stellar mass black holes formed from the collapse of individual massive stars, the kind that might have a mass of 10 or 20 or even 100 times that of our Sun. Supermassive black holes contain millions or even billions of times the mass of our Sun, all concentrated in a region smaller than our solar system. The black hole at the center of the Milky Way, called Sagittarius A, pronounced Sagittarius A star, weighs about 4 million solar masses. That's 4 million times the mass of our Sun, all packed into a region perhaps 50 times the diameter of the Sun itself. The black hole powering Alcyoneus is estimated at around 400 million solar masses, 100 times more massive than the one at the center of our galaxy. Porphyrion's central black hole is thought to be even more massive still, perhaps approaching several billion solar masses. A black hole is, at its most basic level, a region of space-time where gravity has become so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. General relativity, Einstein's theory of gravity, predicts that when enough mass becomes concentrated in a small enough region, it will inevitably collapse into a singularity, a point of infinite density where our normal understanding of physics breaks down. Around this singularity, space-time itself is so severely warped that it creates a one-way surface. Anything that crosses the event horizon is doomed to fall inward, eventually reaching the singularity. The size of a black hole's event horizon is directly proportional to its mass. For a black hole with the mass of our Sun, the event horizon would be about 6 kilometers in diameter, roughly the size of a small city. For Sagittarius A, with its 4 million solar masses, the event horizon is about 17 times the diameter of the Sun, about the distance from the Sun to Mercury's orbit. For the supermassive black holes that power giant radio galaxies, the event horizons can be larger than the orbit of Neptune. Entire planetary systems could fit within them. But black holes aren't just cosmic vacuum cleaners, indiscriminately swallowing everything around them. Despite their popular depiction in movies and television, they're actually quite selective eaters. For a black hole to consume material, that material needs to get very close to it, close enough that the black hole's gravity can overcome the material's orbital motion. Most of the matter in a galaxy orbits the black hole at safe distances, just as planets orbit the Sun without falling into it. The Sun's gravity doesn't pull the planets inward because they have orbital velocity. They're moving sideways fast enough that as they fall toward the Sun, they also move around it, creating a stable orbit. However, sometimes gas and dust do fall toward the black hole. Perhaps the galaxy experiences a gravitational interaction with a neighboring galaxy, stirring up gas and causing it to lose its orbital energy. Perhaps two galaxies merge, funneling vast amounts of gas toward the central black hole. Perhaps a star wanders too close and gets torn apart by tidal forces. with half its mass falling toward the black hole. Or perhaps gas just gradually loses energy through normal processes, cooling and falling into the gravitational well at the galaxy's center. When matter falls toward a black hole, it doesn't plunge straight in. Instead, due to conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull their arms in, it forms a flattened disk of material swirling around the black hole, much like water circling a drain. This structure is called an accretion disk, and it's one of the most violent environments in the universe. As material in the disk spirals inward, it rubs against neighboring material, creating friction. This might sound innocuous, like rubbing your hands together on a cold day to warm them up, but the speeds involved are extraordinary. Material in the inner accretion disk can be orbiting at substantial fractions of the speed of light. The friction generated by this motion heats the disk to tremendous temperatures, often millions of degrees in the innermost regions. At these temperatures, the disk doesn't glow in visible light like the surface of a star. It glows in ultraviolet light and X-rays, higher energy forms of radiation that our eyes can't see but that space telescopes can detect. The accretion disk around a supermassive black hole can outshine the entire galaxy that hosts it, with the combined light of billions of stars being outshone by a region smaller than our solar system. Now here's where things get truly extraordinary, and where radio galaxies come into the picture. Not all the material in the accretion disk falls into the black hole. Some of it, perhaps 5 to 10%, gets caught up in the intense magnetic fields that thread through the disk and the spinning space-time around the black hole itself. These magnetic fields are created and amplified by the swirling motion of the charged particles in the disk. Ionized gas, plasma containing free electrons and ions, moves through space and naturally generates magnetic fields. As the disk rotates, it twists and amplifies these fields, creating structures that extend above and below the disk's plane. Near the black hole, where space itself is rotating due to the black hole's spin, a process called frame dragging, these magnetic fields can tap into the rotational energy of the black hole or the orbital energy of the innermost disk material. These magnetic fields act like cosmic particle accelerators and channels. They grab material from the inner regions of the accretion disk and fling it outward in two narrow beams, perpendicular to the disk, along the black hole's rotational axis. Imagine standing above the north pole of the black hole's accretion disk. You'd see a narrow beam of material shooting straight up away from the disk. If you could somehow look down through the black hole to its south pole, you'd see another beam shooting downward, creating a mirror image. These beams, or jets, are among the most powerful and long-lived phenomena in the universe. The material in the jets travels at substantial fractions of the speed of light, often exceeding 90 to 9% of light speed. At these velocities, Einstein's special theory of relativity becomes crucial for understanding their behavior. Time slows down for the particles in the jets, lengths contract in the direction of motion, and mass increases. We call them relativistic jets because at these velocities, relativistic effects dominate. The exact mechanism by which black holes and their accretion disks produce jets is still not fully understood, and it remains one of the major open questions in astrophysics. How does a black hole, a region from which nothing can escape, produce jets that shoot material outward at nearly the speed of light? The answer lies not in material escaping from inside the event horizon, that's impossible, but in energy being extracted from the region just outside the event horizon and from the accretion disk itself. Two main theoretical frameworks have been proposed to explain jet formation, and both are named after the astrophysicists who developed them. The Blandford-Znajek mechanism, proposed by Roger Blandford and Roman Zajac in 1977, suggests that the black hole's rotation can be tapped to extract energy. In this model, magnetic field lines threading through the black hole's event horizon can transfer rotational energy from the spinning black hole itself into the jets, like a cosmic generator, converting rotational energy into the kinetic energy of particles streaming away in the jets. The Blandford-Payne mechanism, proposed by Roger Blandford and David Payne in 1982, focuses instead on the accretion disk. It suggests that magnetic fields anchored in the disk can extract energy and angular momentum from the disk material and redirect it into jets. Material in the disk, moving in circular orbits, is caught by the magnetic field and channeled upward and outward along field lines that are inclined relative to the disk, converting orbital energy into outward motion. In reality, both mechanisms probably contribute to jet formation, with their relative importance depending on factors like the black hole's spin rate and the properties of the accretion disk. A rapidly spinning black hole can extract more energy through the Blandford-Zajac mechanism, while a thick, gas-rich accretion disk might favor the Blandford-Payne mechanism. The jets don't just shoot out into empty space and disappear. As they travel away from the black hole, they plow into the surrounding environment, the gas that fills the space within and around the galaxy. This interaction creates structure and reveals the jet's presence. Near the black hole, the jets are narrow and collimated, tightly focused beams of particles and magnetic fields, sometimes only a few light years across, despite extending for millions of light years. The magnetic fields in the jets act like invisible walls, constraining the material and preventing it from spreading out. As the jets travel farther from the black hole, they begin to spread and slow down, eventually inflating enormous lobes or plumes of radio-emitting plasma. These lobes are what LOFAR detected when it discovered Alcyoneus and Porphyrion. The plasma in these lobes consists of electrons and positively charged ions, all moving at high speeds. When these charged particles spiral around magnetic field lines, a motion forced on them by the magnetic field structure, they emit synchrotron radiation. This process, named after particle accelerators called synchrotrons, where it was first observed in laboratories in the 1940s and 50s, produces radiation across a broad range of wavelengths, but it's particularly strong at radio frequencies. This is why we call these objects radio galaxies. They're not necessarily producing more total energy than other galaxies, but they're converting a significant fraction of their energy output into radio waves that we can detect with radio telescopes. The radio emission from the lobes can be thousands of times stronger than all the radio emission from all the stars in the galaxy combined. Radio astronomers classify radio galaxies into different types based on their structure and properties. The most widely used classification system was developed by Bernard Phaneroff and Julia Riley in 1974, based on their analysis of radio galaxies detected in surveys conducted in the late 60s and early 70s. They noticed that radio galaxies seem to fall into two distinct classes based on the distribution of their radio brightness. Class 1, or Phaneroff-Riley I, or free, objects are brightest toward their centers. Their jets are easily visible in radio images, but they seem to lose energy as they travel outward, creating diffuse plumes rather than sharp lobes. The jets in FRI sources often show a complex meandering structure, suggesting they're being buffeted or disrupted as they travel through the surrounding gas. Class 2, or Phaneroff-Riley II, or Fry, objects like Alcyoneus and Porphyrion are brightest at their edges. Their jets are often difficult to detect in the inner regions, appearing as faint threads or sometimes not visible at all. But they terminate in bright, hot spots where the jet material slams into the surrounding medium, like a fire hose hitting a wall. Free radio galaxies tend to be more powerful than free galaxies and they can maintain their jets over much greater distances. The division between free and free occurs at a radioluminosity of about 10 to the power of 10 power of watts per hertz at a frequency of 178 megahertz. Above this threshold, most radio galaxies are free. Below it, most are free. This suggests that the power of the jets determines their structure, with more powerful jets able to punch through the surrounding gas and maintain their collimation to large distances. The environment through which these jets travel plays a crucial role in determining how large a radio galaxy can grow. Jets traveling through dense gas will be slowed and disrupted relatively quickly. The jet material transfers its energy to the surrounding gas, heating it and pushing it aside, but in doing so, loses its own energy. Dense gas creates more resistance, shortening the distance that jets can travel. But jets traveling through thinner environments can extend much farther before their energy is dissipated. It's like the difference between running through water and running through air. In water, you encounter much more resistance and can't maintain your speed for long. In air, you can run much farther with the same amount of energy. This is part of why Alcyoneus is such a puzzle. The galaxy itself doesn't appear particularly special when you look at its visible light emission. Its stellar mass, the total mass of all the stars it contains, is actually somewhat below average for giant radio galaxies. Most of the giant radio galaxies discovered in the same survey are hosted by galaxies with more stars, more mass, and presumably more gas to fuel their central black holes. Its central black hole, while massive at 400 million solar masses, isn't unusually so for a galaxy of its type. There are plenty of other galaxies with black holes of similar or greater mass. The jets don't appear to be particularly powerful compared to other radio galaxies. Their radioluminosity is substantial, but not exceptional. So what makes Alcyoneus special? One possibility is that it simply resides in a less dense region of space, where the intergalactic medium offers less resistance to the jet's expansion. If Alcyoneus happens to be in a region where the gas density is lower than average, its jets could travel farther with the same amount of energy, inflating larger lobes. Another possibility is related to viewing angle, though this seems less likely. If the jets are pointed almost directly along our line of sight, we'd be looking down the barrel of the jet, and what appears to be a large structure on the sky might actually be much longer in three-dimensional space, just foreshortened by perspective. But detailed analysis of Alcyoneus suggests that the jets are actually fairly close to perpendicular to our line of sight, oriented across the sky rather than toward or away from us. So projection effects don't explain Alcyoneus's size. Yet another possibility is related to time. Radio galaxies aren't eternal. The jets turn on when the black hole is actively feeding, and they turn off when the fuel supply is interrupted or exhausted. A typical radio galaxy might remain active for a few 100 million years before the jets shut down. During this time, the jets are continuously pumping energy into the lobes, pushing them outward and inflating them to larger and larger sizes. But if the black hole has access to a particularly abundant and steady supply of gas, the jets might remain active for much longer. The longer the jets stay on, the farther they can travel, and the larger the radio lobes can grow. Perhaps Alcyoneus simply represents a radio galaxy that's been active for an unusually long time, perhaps 1 billion years or more, allowing its lobes to grow to record-breaking sizes. This possibility is supported by observations of Alcyoneus's host galaxy, which shows signs of recent activity, but no obvious merger or other event that would provide a sudden influx of gas. It suggests a steady, long-term accretion process, rather than a dramatic feeding event. The discovery of Porphyrion added another piece to this puzzle. Porphyrion is even larger than Alcyoneus, but it exists in the distant universe when conditions were different. The universe was denser, Galaxy collisions were more common, and black holes were growing more rapidly. Yet Porphyrion managed to grow its jets to 23 million light-years, suggesting that the conditions for creating these giant structures existed even in the early universe. The cosmic web connection, structure on the largest scales to truly understand the significance of Alcyoneus, Porphyrion, and TXS 0033 plus 252, we need to zoom out even further and consider their place in the largest structures known to exist, the cosmic web. When astronomers map the distribution of galaxies across the universe, plotting the positions of millions of galaxies in three-dimensional space, they don't find them scattered randomly like grains of sand on a beach or stars against the night sky. Instead, galaxies are organized into an intricate pattern that resembles a three-dimensional spider's web or perhaps the structure of soap bubbles packed together. There are dense knots where galaxy clusters congregate, containing hundreds or thousands of galaxies bound together by their mutual gravity, all orbiting around their common center of mass. These clusters are the largest gravitationally bound structures in the universe, regions where gravity has won out over the expansion of the universe itself, pulling galaxies together and holding them in place. From these clusters, long filaments of galaxies stretch out across hundreds of millions of light-years, like threads connecting the knots in a web or the edges where soap bubbles meet. These filaments contain not just galaxies but also vast amounts of diffuse gas, the warm, hot intergalactic medium that holds most of the ordinary matter in the universe. Between the filaments lie vast voids, enormous regions that contain few, if any, galaxies, empty bubbles in the cosmic foam that can be hundreds of millions of light-years across. These aren't truly empty. They contain some dark matter and very diffuse gas, but they're remarkably devoid of galaxies compared to the filaments and clusters. If you were somehow transported to the center of one of these voids, looking out in any direction, you might not see another galaxy for hundreds of millions of light-years. This cosmic web wasn't always so apparent to astronomers. Through most of the 20th century, they knew that galaxies clumped together in clusters, massive concentrations like the Virgo cluster with its thousands of galaxies. But they thought these clusters were more or less randomly distributed through space, with no larger organizing principle. The first hints that something more organized was going on came in the 1980s, when astronomers began conducting large-scale surveys that measured the distances to thousands of galaxies using spectroscopy. By measuring how much the light from each galaxy had been redshifted by the expansion of the universe, they could determine how far away each galaxy was, allowing them to map the universe in 3 dimensions rather than just seeing galaxies projected on the 2-dimensional sky. One of the most famous early visualizations of the cosmic web came from a survey conducted by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. In 1989, they published a slice through the universe showing the distribution of galaxies within a wedge of sky extending out to about 600 million light-years. The results were stunning, completely unexpected. Galaxies traced out an unmistakable bubble-like structure with dense walls surrounding nearly empty voids. One particularly prominent feature, a long curved string of galaxies that Geller and Huchra dubbed the Great Wall, stretched across the survey region like a cosmic highway. The Great Wall appeared to be about 500 million light-years long, 200 million light-years wide, and only 15 million light-years thick, an immense sheet of galaxies. When Geller and Huchra presented their results at scientific conferences, astronomers were astonished. This wasn't what the prevailing theories had predicted. The structure was too large, too organized, It challenged ideas about how the universe evolved and how structures formed from the nearly uniform early universe. Since then, larger and deeper surveys have mapped the cosmic web in ever greater detail. The Sloan Digital Sky Survey, which began operating in 2000 and continues to this day, has measured distances to millions of galaxies, allowing astronomers to map the large-scale structure of the universe out to billions of light years. The cosmic web is now understood to be one of the fundamental organizing principles of the universe, a structure that encompasses everything from individual galaxies to the largest known structures. But what creates the cosmic web? Why is the universe organized this way, rather than having galaxies distributed smoothly throughout space? The answer lies in the universe's history and in the mysterious substance called dark matter. According to our current understanding, based on observations of the cosmic microwave background, the afterglow of the Big Bang, and many other lines of evidence, the universe began 13.8 billion years ago in an event that brought space, time, matter, and energy into existence in an unimaginably hot and dense state. In those first moments, fractions of a second after the Big Bang, the universe was remarkably smooth and uniform, with matter distributed almost evenly throughout space. The density varied by only a few parts per 100,000 from one region to another, but not quite evenly. There were tiny variations in density, quantum fluctuations from the earliest instance that had been stretched to cosmic scales by a brief period of exponential expansion, called inflation. These tiny density variations, differences of only a few parts per 100,000, were the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter toward them. As more matter accumulated, their gravity became stronger still, attracting even more matter in a runaway process. Meanwhile, regions that were slightly less dense than average lost matter to the growing dense regions, becoming the voids we see today. But visible matter, the stuff that makes up stars, planets, gas clouds, and people, constitutes only about 15% of the total matter in the universe. The remaining 85% is dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We don't know what dark matter is made of. It's not made of atoms like ordinary matter. It doesn't interact with light or with ordinary matter except through gravity. We know dark matter exists because we can see its gravitational effects. Galaxies rotate faster than they should based on the visible matter they contain, suggesting there's much more mass present than we can see. Galaxy clusters hold together despite moving too fast to be bound by the gravity of their visible matter alone. Light from distant galaxies is bent more than it should be as it passes through clusters, indicating the presence of additional mass. And the cosmic microwave background shows patterns that can only be explained if the universe contains far more matter than we can see. Without dark matter's gravity, galaxies would spin themselves apart, their outer stars flying off into intergalactic space. Without dark matter, the cosmic web would look completely different. The structures we see today wouldn't have had time to form in the 13.8 billion years since the Big Bang. Dark matter played the dominant role in shaping the cosmic web. Because dark matter doesn't interact with light or with itself through any force except gravity, it could begin clumping together earlier and more efficiently than visible matter. While visible matter was still being buffeted by radiation pressure in the early universe, kept smooth by the pressure of photons pushing against it, dark matter was already collecting in dense halos, forming the gravitational scaffolding along which visible matter would later flow. Computer simulations of cosmic structure formation, which track the evolution of millions or billions of dark matter particles through billions of years of cosmic history, beautifully reproduce the web-like structure we observe. These simulations start with the tiny density fluctuations measured in the cosmic microwave background and evolve them forward in time using the laws of gravity. The simulations show dark matter collecting along filaments, with the densest concentrations at the intersections where multiple filaments meet. These intersections become galaxy clusters. The filaments themselves act as highways, channels along which gas flows from the voids toward the clusters. Over billions of years, the structure becomes more and more pronounced, with the dense regions getting denser and the voids getting emptier. This is where radio galaxies like Alcyoneus come into the picture. Alcyoneus resides in a filament of the cosmic web, though not a particularly dense one. Its radio lobes, stretching 16 million light-years, extend through this filament, potentially interacting with the gas that threads through the cosmic web structure. The jets from Alcyoneus aren't just shooting into empty space. They're plowing through the intergalactic medium, the dilute gas that fills the space between galaxies. This intergalactic medium is extraordinarily tenuous compared to anything we experience on Earth. In the voids between filaments, there might be only a few atoms per cubic meter, far less than 1 particle per cubic centimeter, making it emptier than the best vacuum we can create in laboratories on Earth. To put this in perspective, the air you're breathing right now contains about 30 million trillion molecules per cubic centimeter. The best laboratory vacuums contain perhaps 10 million molecules per cubic centimeter. The vacuum of space near Earth in low Earth orbit contains about 1 million particles per cubic centimeter. But in the voids of the cosmic web, there might be only 1 particle per 10 cubic centimeters, or even less. In the filaments, the density is somewhat higher, perhaps 100 atoms per cubic meter, 10 per cubic centimeter. This is still incredibly tenuous, still a far better vacuum than we can create in laboratories. But over the vast distances these jets travel, even this tenuous gas can have significant effects. As the jets from Alcyoneus travel through the intergalactic medium, they're like cosmic snowplows, pushing gas aside and creating bubbles of hot, shocked plasma. Where the jet material meets the surrounding gas, shock waves form, sudden discontinuities where the gas is compressed and heated. This interaction heats the gas to temperatures of millions of degrees, causing it to glow in X-rays that space telescopes can detect. The jets also inject energy and magnetic fields into the intergalactic medium, influencing conditions across enormous volumes of space. The energy injected by radio galaxies can heat the gas in filaments, preventing it from cooling and condensing to form new galaxies. This process, called AGN feedback, where AGN stands for active galactic nucleus, the term astronomers use for an actively feeding supermassive black hole, is thought to be one of the main reasons why galaxy formation shut down in massive galaxies. The magnetic fields carried by the jets seed the magnetism we detect in galaxy clusters and perhaps even in the filaments themselves. Before the discovery of these giant radio galaxies, it was unclear how the cosmic web became magnetized. Stars and galaxies have magnetic fields generated by rotating plasma. But how did these fields get out into the vast reaches of intergalactic space? Giant radio galaxies provide a mechanism. Their jets can carry magnetic fields from the galaxy out into the cosmic web over distances of millions or tens of millions of light years. This interaction goes both ways. The intergalactic medium also affects the jets. If the jets encounter a region of denser gas, they can be slowed or deflected, their progress impeded by the increased resistance. If the medium has flows or currents, like winds in Earth's atmosphere, these can bend the jets, creating curved or twisted structures. Some radio galaxies show highly asymmetric lobes, with one side much larger or brighter than the other. This asymmetry can arise if one jet is traveling into a headwind while the other has a tailwind, if the galaxy is moving through the intergalactic medium, or if the medium itself has bulk flows. One jet might encounter more resistance than the other, leading to differences in how far each can extend. For Alcyoneus, residing in a cosmic web filament means its jets experience a sort of cosmic environment that shaped their growth. Gas in the filament might be flowing in certain directions, creating conditions that favored the jet's expansion. The relative emptiness of the particular region Alcyoneus occupies might explain why its jets could travel so far. The discovery of Porphyrion added another layer to this picture. Porphyrion exists in the distant younger universe when the cosmic web structure was still developing. At that epoch, when the universe was only 6.3 billion years old, about half its current age, the cosmic web was more compact. The filaments were closer together, and the voids between them were smaller. For Porphyrion's jets to reach 7 megaparsecs in this more compact cosmic web means they extended across an even larger fraction of the universe's structure at that epoch. The jets reached about 2/3 of the way across a void, a truly cosmological scale. They weren't just affecting the galaxy's immediate surroundings, they were reaching across cosmic structures, potentially influencing the evolution of the cosmic web itself. This suggests that giant radio galaxies like Alcyoneus and Porphyrion aren't just interesting objects in their own right. They're potentially important players in the evolution of the cosmic web itself. Bridges between the microscopic world of black holes and accretion disks and the cosmic scale structure of the universe. The energy they inject into the intergalactic medium can heat gas over vast volumes, preventing it from cooling and condensing to form new galaxies. This could help explain why we don't see as many large galaxies as simple models would predict. The jets from supermassive black holes, acting over billions of years, might have suppressed galaxy formation across significant volumes of the universe. The magnetic fields they inject can seed the magnetism we detect in galaxy clusters and filaments. Observations of galaxy clusters show that they contain magnetic fields with strengths of about 1 microgauss, about 1,000,000 times weaker than Earth's magnetic field, but spread over millions of light years. The origin of these fields has been mysterious. Giant radio galaxies might be the source, jets from billions of years of black hole activity having magnetized the cosmic web. These jets might also play a role in enriching the intergalactic medium with heavy elements heavier than hydrogen and helium, that were created in stars and supernovae. When jets interact with the gas in their host galaxy, they can sweep up material and carry it out into intergalactic space, distributing the products of stellar nucleosynthesis across cosmic scales. All of this paints a picture of radio galaxies not as isolated phenomena, but as cosmic scale processes that connect individual galaxies to the large-scale structure of the universe. A supermassive black hole, an object that might be only a few light hours across, can influence structures spanning tens of millions of light years, reaching across voids and filaments, shaping the evolution of the cosmic web itself. Comparing giants, different measures of size. When we talk about the largest galaxies in the universe, it's important to understand that we can measure size in different ways, and different measurement methods give different answers. This is part of why there's sometimes confusion about which galaxy holds various records. Let's return to IC 1101, the supergiant elliptical galaxy we mentioned earlier. In terms of its stellar content, the number and distribution of stars it contains, IC 1101 is truly immense. It's one of the largest galaxies known when we measure size based on starlight. IC 1101 sits at the center of the Abell 2029 galaxy cluster, one of the most massive galaxy clusters known, located about 1 billion light-years from Earth, in the constellation Serpens. As the central dominant galaxy in this cluster, IC 1101 has grown through the gradual accumulation of smaller galaxies that have merged with it over billions of years, a process called galactic cannibalism. The galaxy's core region, where most of its stars are concentrated, spans about 400,000 to 600,000 light-years. To put this in perspective, you could fit 4 to 6 Milky Way galaxies side by side within IC 1101's core alone. The galaxy contains approximately 100 trillion stars, about 1,000 times more than our Milky Way's few hundred billion stars. If every star in the Milky Way were a person, IC 1101 would have enough stars to represent all the people who have ever lived on Earth, many times over. But IC 1101 doesn't stop at its bright core. Like most elliptical galaxies, it's surrounded by an extensive stellar halo, a diffuse cloud of stars that extends far beyond the bright central regions. This halo gets fainter and fainter as you move outward, gradually fading into the background light of the galaxy cluster. The exact size of this halo depends on how faint a glow you can detect, which depends on how sensitive your telescope is. With very sensitive observations, astronomers have detected starlight from IC 1101 extending out to about 2 million light-years from the galaxy's center. At these distances, the starlight is incredibly faint, perhaps 1/10 the brightness of the night sky on Earth, but it's detectable with modern instruments. If we count this diffuse halo, IC 1101 might span about 4 million light-years in diameter. But there's more. IC 1101 sits in the center of a galaxy cluster, surrounded by intra-cluster light, the diffuse glow of stars that have been stripped from galaxies and now wander between galaxies in the cluster. Some of these stars might have originally belonged to IC 1101 or to galaxies that merged with it. Others come from other galaxies in the cluster that have had close encounters, tidal interactions that pulled stars away. This intra-cluster light can extend across the entire cluster, millions of light-years. Should we count this intra-cluster light as part of IC 1101's size? It's a matter of definition. If we're asking how far IC 1101's gravitational influence extends, or what volume of space has been affected by IC 1101's growth and evolution, then perhaps we should. But if we're asking about the galaxy itself, the bound system of stars orbiting a common center, then probably not. This ambiguity is part of why there's been confusion about IC 1101's size. Different sources quote different numbers, from about 500,000 light-years to 6 million light-years or more, depending on what they're measuring and how they define the galaxy's edge. Now compare this to Alcyoneus, Porphyrion, and TXSSO33 plus 252. When we measure their sizes, we're not measuring the extent of their starlight at all. We're measuring the extent of their radio emissions, the lobes of plasma inflated by their jets. These lobes extend far beyond any reasonable definition of the galaxy itself. The visible galaxy at the center of Alcyoneus, the collection of stars that makes up the galactic bulge and any disk or halo it might have, is probably only about 100,000 light-years across, similar to the Milky Way. The galaxy isn't particularly remarkable in terms of its stellar content, but the radio lobes extend more than 8 million light-years from the galaxy's center, giving a total structure size of more than 16 million light-years. In other words, the ratio between the size of Alcyoneus's radio lobes and the size of its visible galaxy is roughly 160 to 1. If you shrunk Alcyoneus's visible galaxy down to the size of a soccer ball, the radio lobes would extend about 1.5 miles in either direction. This illustrates an important point. When we say Alcyoneus or Porphyrion or TXS0033 plus 252 is the largest galaxy, we're really talking about the largest structure created by a galaxy. These structures are not composed of stars, but of extremely diffuse plasma injected into intergalactic space by powerful jets from a central supermassive black hole. While the visible part of a galaxy like Alcyoneus is only about 100,000 light-years across, similar to our Milky Way, its radio lobes extend for millions of light-years. This means the influence of a single black hole can reach across the cosmic web, spanning distances that dwarf the galaxies themselves, and bridge the gap between individual star systems and the large-scale structure of the universe. Implications and the future. When we say Alcyoneus or Porphyrion or TXS 0033 plus 252 is the largest galaxy, we're really talking about the largest structure created by a galaxy. This distinction is profound because it forces us to reconsider the true reach of a single celestial object. We are witnessing the signature of a cosmic engine that defies our traditional maps of the sky. These discoveries are not merely about breaking records. They are fundamental clues that are reshaping our entire understanding of how black holes evolve over eons. For a long time, we viewed supermassive black holes as isolated residents of galactic centers, occasionally consuming nearby gas or stars, but the existence of structures like Porphyrion, which spans 23 million light-years, tells a story of persistent, long-term power. The sheer scale of these jets implies that the black holes at their hearts have been active for immense periods. In Porphyrion's case, perhaps 1 billion years. This challenges the standard models of black hole growth. We used to think that the most powerful jets only came from black holes in jet mode, where energy is primarily channeled into kinetic motion. However, the discovery that Porphyrion was powered by a black hole in radiative mode, one that also emits intense radiation from its accretion disk, suggests that these cosmic giants are far more versatile and common than we ever dared to imagine. It means that throughout cosmic history, even when the universe was less than half its current age, these black holes were already reaching out across the void to claim their territory in the cosmic web. This has massive implications for our theories of galaxy formation. We have often wondered why we don't see as many massive galaxies in the universe as our basic physical models predict. The answer likely lies in AGN feedback. The energy injected by these enormous radio lobes can heat the surrounding intergalactic gas to millions of degrees, preventing it from cooling and falling into galaxies to form new stars. Essentially, a single black hole can act as a cosmic thermostat, regulating the growth of its entire neighborhood and even suppressing the birth of future generations of stars across vast volumes of space. These jets also serve as the universe's delivery system, carrying magnetic fields and heavy elements, the building blocks of life, from the heart of a galaxy out into the distant filaments of the cosmic web. Imagine the universe as a vast, dark ocean, and these galaxies as lighthouse beams that don't just illuminate, but actually warm and stir the waters around them. By studying these giants, we are learning how the metabolism of a black hole affects the health and growth of its host galaxy and the surrounding environment. It's a delicate balance of creation and destruction, where the same forces that prevent new stars from forming are also responsible for enriching the voids with the materials needed for future complexity. As we look toward the future, we are only beginning to scratch the surface. Current surveys like LOFAR have covered only about 1/8 of the sky. If we found Alcyoneus and Porphyrion in such a small window, imagine what awaits us when we scan the entire heavens. New instruments, such as the Square Kilometer Array, SKA, will soon join the hunt, offering even greater sensitivity to the faint, diffuse whispers of these radio giants. We are standing at the threshold of a new era of discovery, where the lynx-eyed technology of tomorrow will reveal that the universe is even more interconnected and majestic than Martinoy or any astronomer before him could have dreamed. Implications and the future. When we say Alcyoneus or Porphyrion or KXS 0033 plus 252 is the largest galaxy, we're really talking about the largest structure created by a galaxy. This distinction is profound because it forces us to reconsider the true reach of a single celestial object. We are witnessing the signature of a cosmic engine that defies our traditional maps of the sky. These discoveries are not merely about breaking records. They are fundamental clues that are reshaping our entire understanding of how black holes evolve over eons. For a long time, we viewed supermassive black holes as isolated residents of galactic centers, occasionally consuming nearby gas or stars. But the existence of structures like Porphyrion, which spans 23 million light-years, tells a story of persistent, long-term power. The sheer scale of these jets implies that the black holes at their hearts have been active for immense periods. In Porphyrion's case, perhaps 1 billion years. This challenges the standard models of black hole growth. We used to think that the most powerful jets only came from black holes in what astronomers call jet mode, where energy is primarily channeled into kinetic motion. However, the discovery that Porphyrion was powered by a black hole in radiative mode, one that also emits intense radiation from its accretion disk, suggests that these cosmic giants are far more versatile and common than we ever dared to imagine. It means that throughout cosmic history, even when the universe was less than half its current age, these black holes were already reaching out across the void to claim their territory in the cosmic web. This realization opens a new chapter in our understanding of black hole evolution. It suggests that the growth of these gravitational monsters is not just about the mass they consume, but about the staggering amount of energy they return to the universe. When we observe Porphyrion at a distance of 7.5 billion light-years, we are seeing a snapshot of the young universe. The fact that such a massive structure could exist at that epoch implies that black holes reached their giant phase much earlier than previously thought. They weren't just passive observers of cosmic history. They were active participants, driving the flow of energy across megaparsecs of space. This leads us to the massive implications for our theories of galaxy formation. We have often wondered why we don't see as many massive galaxies in the universe as our basic physical models predict. The answer likely lies in a process called AGN feedback. The energy injected by these enormous radio lobes can heat the surrounding intergalactic gas to millions of degrees, preventing it from cooling and falling into galaxies to form new stars. Essentially, a single black hole can act as a cosmic thermostat, regulating the growth of its entire neighborhood and even suppressing the birth of future generations of stars across vast volumes of space. The impact of this feedback is difficult to overstate. Imagine a galaxy trying to grow by pulling in nearby gas, only to have that gas blasted away and heated by jets that extend far beyond the galaxy's own borders. This relationship between the central black hole and its wider environment suggests a form of cosmic self-regulation. Without the intervention of these giant jets, galaxies might have grown to even more bloated proportions, potentially destabilizing the delicate balance of the cosmic web. By studying Alcyoneus and its successors, astronomers are beginning to map the limits of galactic growth. Furthermore, these jets serve as the universe's delivery system, carrying magnetic fields and heavy elements, the building blocks of complexity. From the heart of a galaxy out into the distant filaments of the cosmic web. Before the discovery of these giant radio galaxies, the origin of magnetism in the vast reaches of intergalactic space was a persistent mystery. We knew that galaxy clusters were magnetized, but we didn't fully understand how those fields got there. Now, we see that giants like TXS 0033 plus 252 spanning 26 million light-years act as cosmic needles, threading the vacuum with magnetic influence. This transport of material is equally vital. Elements heavier than hydrogen and helium are forged in the hearts of stars and scattered by supernovae. However, these elements often remain trapped within the gravitational pull of their home galaxies. Giant radio jets provide an escape route. They sweep up this enriched gas and carry it out into the intergalactic medium, essentially seeding the universe with the materials that might one day form new stars, planets, and perhaps even life in regions that would otherwise remain barren. As we look toward the future, we are only beginning to scratch the surface of this hidden population. The discovery of Alcyoneus was serendipitous, a byproduct of a different investigation. This suggests that the universe may be teeming with even larger structures that we simply haven't had the tools to see until now. Current surveys like LOFAR have covered only about 1/8 of the sky. Within that small slice, we have already found thousands of giant radio galaxies, each one a potential record breaker. The next generation of telescopes will transform this search into a systematic exploration. The Square Kilometer Array, or SKA, will be one of the most powerful scientific instruments ever built. By combining thousands of antennas across Australia and South Africa, the SKA will offer a level of sensitivity and resolution that dwarfs our current capabilities. It will be able to detect the faintest whispers of radio emission from the very first black holes to form in the universe, allowing us to trace the history of these giant structures back to the cosmic dawn. Other upcoming missions, like the Euclid Space Telescope and the Vera C. Rubin Observatory, will provide the optical data needed to identify the host galaxies of these radio giants across the entire sky. By combining radio observations with precise distance measurements and stellar maps, we will be able to build a complete three-dimensional census of the cosmic web's largest residents. We will no longer be stumbling upon giants by accident. We will be mapping the entire megafauna of the cosmos. These future discoveries will likely answer the questions that Alcyoneus and Porphyrion have raised. We will learn if every large galaxy goes through a giant phase, or if these structures require a rare alignment of black hole spin, fuel supply, and environmental emptiness. We will see how these jets interact with the dark matter scaffolding of the universe, and whether they truly have the power to reshape the filaments of the cosmic web itself. We are standing at the threshold of a new era of discovery, where the link-side technology of tomorrow will reveal that the universe is even more interconnected and majestic than Martin Oy, or any astronomer before him, could have dreamed. The discovery of these giants reminds us that the cosmos still has the power to surprise us, to shatter our scales of measurement, and to remind us that we are just beginning to understand the true nature of our home among the stars. The discovery of these gargantuan structures does more than just fill a spot in the record books. It fundamentally alters our timeline of the universe's growth. When we look at Porphyrion, we are seeing it as it existed when the universe was less than half its current age. This presence of such highly organized, massive energy outflows in the relatively early universe suggests that supermassive black holes reach their peak performance much sooner than we once thought. It implies that the conditions in the early cosmos, perhaps the higher density of gas or the specific way dark matter filaments were arranged, were perfectly tuned to allow these black holes to become cosmic architects. We are forced to ask, was this a common phase for all large galaxies? Or is this an elite club of cosmic giants? This leads us to the heart of galaxy formation theories. For decades, astronomers have been puzzled by the cooling flow problem. In theory, the gas in the center of large galaxy clusters should cool down and fall into the central galaxies, creating a massive surge of star formation. But we don't see this happening. The stars aren't there in the numbers they should be. The existence of Alcyoneus and Porphyrion provides a dramatic visual answer to this mystery. These jets aren't just shouting into the void. They are physically pushing, heating, and stirring the intergalactic medium. They act as a massive cosmic blower, clearing out the nursery of the galaxy and ensuring that the star-forming material remains too hot to ever settle. By studying these giants, we are effectively watching the brakes of galactic evolution in action. But the influence of these jets extends even further, beyond the heating of gas. They are the primary distributors of cosmic magnetism. Space is not truly empty. It is permeated by faint magnetic fields that guide the movement of cosmic rays and shape the flow of matter. For a long time, we didn't know how these fields reach the vast, empty voids between galaxies. Now, we have our smoking gun. A single event at the heart of a galaxy, the spinning of a black hole, can launch a magnetic influence that travels for 26 million light-years. These giants are the threads that weave the electromagnetic fabric of the cosmic web. They link the smallest points of space-time, the singularity of a black hole, to the largest scales of the universe's structure. The future of this research is as vast as the galaxies themselves. We are currently in what many call the golden age of radio astronomy. Instruments like LOFAR, which discovered Alcyoneus, are just the beginning. The upcoming Square Kilometer Array, SKA, will be a revolutionary step forward. Imagine a telescope so sensitive that it could detect a single airport radar on a planet orbiting a star tens of light years away. When we turn that sensitivity toward the deep sky, we won't just see the bright heads of these jets. We will see the faint, ghostly tails and the relic lobes of galaxies that died billions of years ago. The SKA will allow us to conduct a cosmic census, identifying how many of these giants are currently active and how many are sleeping giants that have left their marks on the universe. Furthermore, these future surveys will help us understand the relationship between these radio giants and the dark web of the universe, the dark matter that makes up most of the cosmos. Does a radio jet prefer to grow along a dark matter filament? Does the density of the surrounding dark matter determine how far a jet can travel before it is stopped? By mapping thousands of these structures, we can use them as probes to feel out the invisible scaffolding of the universe. We are moving from a time of individual discoveries to a time of cosmic cartography, where we map the veins and arteries of the universe's energy flow. As our technology improves, we might even find that Alcyoneus and Porphyrion are mid-sized compared to what lies in the furthest, darkest corners of the sky. Every time we build a better lens, the universe reveals a larger scale. This tells us a profound truth about science. The more we know, the more we realize how much is still hidden in the light we haven't yet seen. We are standing on the shore of a vast, dark ocean, and we have only just begun to see the ripples of the largest creatures that inhabit its depths. The discovery of these gargantuan structures does more than just fill a spot in the record books. It fundamentally alters our timeline of the universe's growth. When we look at Porphyrion, we are seeing it as it existed when the universe was less than half its current age, only 6.3 billion years old. This presence of such highly organized, massive energy outflows in the relatively early universe suggests that supermassive black holes reached their peak performance much sooner than we once thought. It implies that the conditions in the early cosmos were perfectly tuned to allow these black holes to become cosmic architects. We are forced to ask, was this a common phase for all large galaxies? Or is this an elite club of cosmic giants? This leads us to the heart of galaxy formation theories. For decades, astronomers have been puzzled by the cooling flow problem, where gas should cool and form stars, yet star formation in massive galaxies often appears shut down. The existence of Alcyoneus and Porphyrion provides a dramatic visual answer to this mystery. These jets aren't just shouting into the void, they are physically pushing, heating, and stirring the intergalactic medium. They act as a massive cosmic thermostat, ensuring that the star-forming material remains too hot to ever settle. By studying these giants, we are effectively watching the breaks of galactic evolution in action, but the influence of these jets extends even further, beyond the heating of gas. They are the primary distributors of cosmic magnetism. Space is not truly empty. It is permeated by faint magnetic fields that shape the flow of matter. For a long time, we didn't know how these fields reached the vast filaments between galaxies. Now, we have our smoking gun. A single event at the heart of a galaxy, the activity of a black hole, can launch a magnetic influence that travels for 26 million light-years. These giants are the threads that weave the electromagnetic fabric of the cosmic web. The future of this research is as vast as the galaxies themselves. We are currently in what many call the golden age of radio astronomy, led by instruments like LOFAR. The upcoming Square Kilometer Array, or SK, will be a revolutionary step forward, offering even greater sensitivity to the faint, diffuse whispers of these radio giants. We will move from a time of individual serendipitous discoveries to a time of systematic mapping. We are moving toward a period of cosmic cartography, where we map the veins and arteries of the universe's energy flow. As our technology improves, we might even find that Alcyoneus and Porphyrion are mid-sized compared to what lies in the furthest, darkest corners of the sky. Every time we build a better lens, the universe reveals a larger scale. This tells us a profound truth about science. The more we know, the more we realize how much is still hidden in the light we haven't yet seen. We are standing on the shore of a vast, dark ocean, and we have only just begun to see the ripples of the largest creatures that inhabit its depths. Closing reflections. As we return from the edges of the cosmic web to the quiet of the present moment, let the scale of these discoveries settle within you. We began this journey by looking at the familiar distances of our own streets and cities, only to find ourselves contemplating structures that light takes 26 million years to cross. It is a journey that brings us full circle, from the human impulse to wonder at the night sky to the realization that we are part of a universe far more vast and active than we ever imagined. The story of Alcyoneus and Porphyrion is not just a story of numbers and light years, it is a story of human curiosity. It reminds us that even a graduate student looking at a computer screen can stumble upon a giant that challenges our understanding of the cosmos. It shows us that there are still secrets hidden in plain sight, waiting for the right moment and the right tools to find them. If you've enjoyed this drift through the depths of the cosmos, consider subscribing to the channel and liking this video to join us on our next journey. Your support helps us continue to explore these wonders together. For now, let the images of graceful radio wings and swirling black holes fade into a peaceful calm. Remember, that while the universe operates on scales that shatter our everyday experience, we are the ones capable of reaching out to understand it. Take one last deep breath, feeling the stillness around you, and carry the wonder of the cosmic giants with you as you drift into a restful sleep. The universe is vast and its stories are infinite, but for tonight, our journey is complete.